Hi folks, we're going to take a couple minutes here to look through the horizontal circles and horizontal paths worksheets and just talk through the logic of each of these questions. That way, in case you have any questions, this will hopefully help out. If you still have questions after watching this, go ahead and just let me know and we'll talk through it individually. So in this first example, we've got a police car going around a curve, and we're asked to analyze it. So part A says to draw a free body diagram showing the forces, not the components exerted on the car as it rounds the corner. Draw them as relative length, blah, 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 and we must start on the dot, move out all the normal free body diagram stuff. So first of all, because we know this is on Earth, we've got a downward gravitational force. So let me try and move that to be a little bit bigger. Let's go with this. So we've got a downwards gravitational force. I guess that's a little too big. That looks good. We've got an upwards normal force. Are these the same? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have force normal, force gravitational. And because it's coming, let's see, so for you it'll be out of the screen and going to the left, then we expect a force in that same direction that'll be providing the centripetal force. In this case, it's the force of friction. So that's what we have here. The up and down force need to be same. The horizontal forces do not, or does not have any necessarily relationship. Okay, so suppose the car enters a wet section of the roadway so that the maximum coefficient of friction is less. What's the maximum safe speed? And mark it with the correct relationship. So if we have less tangential force, then that means that there's not as much pulling me inwards, which means I'm going to be accelerating less, which means that I can't turn as tightly. So in other words, the new speed has to be less than the old speed. And the logic here is what I had just said. So smaller mu means, and I'm writing this shorthand. If you were writing it on the test, you'd want to write it a bit clearer, but because we're kind of talking through it as well, that leaves me some play there. Means smaller force of friction, which means not as much acceleration, which means we need to slow down. So because the acceleration essentially determines the tightness of your turn, if you're going slower, then you've got kind of longer time to turn over, and you can have a situation where that works. So in other words, the amount that the velocity can change with a smaller acceleration is smaller. So we need to have a lower velocity because we don't need to change the angle as quickly. Next, we come to suppose the car arrives at another section of roadway that also curves but has a radius of curvature greater than r. The maximum safe speed is v2, and mark this. So now we have the opposite, where if it's a bigger curve, we don't need to turn as quickly because it's a larger radius. So if we don't need to turn as quickly, we don't need as much acceleration, then we can basically have a higher speed because we don't need that relationship there. So bigger r means less quick change of the velocity. So we can if there's less quick of a change of velocity because we have the same frictional force, we can still have room for higher v. So if we have a larger radius, that means if you want to think about it, it's a straighter curve. It's a straighter line, any given section. So you can move with a faster speed with the same change in angle provided by the acceleration and still stay on the road. Okay, quantitative analysis, derive an expression for the maximum space speed that the car can take in terms of mu and r. So there's some flexibility here of how you can write this out, but I'm going to show one example. So we want to start with the net force is equal to the mass times the centripetal acceleration. And so this is also going to be the net force is equal to mv squared over r. And we know that that net centripetal force is just going to be the force of friction. And that force of friction is mu mg times mv squared over r. Mu is equal to, mu g is equal to v squared over r. Mu is equal to the, we wanted to solve for v. So then we can algebraically rearrange to get v is equal to the square root of mu g r. And the explanation, you can go back through and explain it. Basically, we started by saying the centripetal force is equal to the mass times the centripetal acceleration. We know that centripetal acceleration can also be written as v squared over r. We know that the only force is the frictional force. We know frictional force is equal to mu mg. We can cancel the mass on both sides, and then we can just algebraically rearrange to get square root of mu g r. So explain how this supports your answer in B1. In B1, we said a smaller mu implies smaller v, which is what we had said. And then in part 2, larger r leads to larger v. So that's hopefully pretty straightforward, tracks well. If you have any questions, let me know. Moving on to our next problem here. We've got a coin on a rotating table. Now, the difference between this one and the last one is, in the last one, the car itself was doing the propulsion, in a sense. So it was, what does the car need to do to be able to stay in its kind of circle? Here, we're asking, how does the situation that the coin is in needs to set itself so that it doesn't slip off. So there's a slight nuanced difference there, but it's largely the same idea. So drawing our free body diagram, it's going to basically be the same. We have a downwards gravitational force, an upwards normal force, and a centripetal force in towards the center, which is going to be a frictional force. Sorry, that's a little sloppy, but you get the idea. Normal force up, gravitational force down, frictional force inwards. So now they've given you the derivation, we need to explain it. Okay, so this is the definition of friction. So that's pretty straightforward. Then if we come down here a bit more, Fn is equal to mg in this case. So that's only in this case, it's not always, but in this case it is. And then we've got the F friction needs to equal the centripetal force, which is equal to mv squared over r. So I'm writing this shorthand. You should probably write in words. The frictional force is providing the centripetal force, which is why it's equal to mv squared over r. And then here we cancel the mass. Next, we've got that the speed must be speed must be less than max speed from centripetal force. So what we've done is we basically algebraically rearranged this to say that the speed squared must be less than ug over r. Because we know that it doesn't slip, so we know that this relationship has to stay constant, which gives us kind of some indication of what the speed will be. And then we can isolate or square root. And that means that if we come back to the plugging that into our previous equation, we can get a where did I slip up here? They're missing a step here that does not help, because we know, I think that this one right here, yeah, this step right here is not particularly clear. I think there's an error in this text. They're missing a step. What we need to know is that v has to also be less than or equal to 2 pi r over t. And this is the speed at edge, defined by just the fact that we've got the total distance of the circumference, 2 pi r, and then t is the period. So that tells us the speed. We can plug that into our equation, and that's where we get this relationship down here. So yeah, this is a little weird. They're missing that step to kind of draw that logic. I think it was supposed to be here based on the solutions guide annotation. And that's just that there's a constant rotation, and so depending on the radius, t is always the same. I wouldn't worry too much about this as long as you track the big picture of it. Okay, so now we've got two people. Blake and Carlos are trying to predict whether the coin will slip if it is too close or too far. And here's their reasoning. So Blake says, I think the coin will slip if it's too close. If the car takes a turn too tightly, the car can slide out of control. There's not enough force if the radius is too small. Carlos says he thinks it'll slip if it's too far. If you ride on the merry-go-round near the center, you don't feel much force. If you ride near the outside, you feel more force pulling you away. So if we look at the previous equation, So if r is small, then the left side is small and it's not likely to slip. As you know, mu g is going to be whatever it is. So the smaller r is, the less likely it is to happen. And then Carlos is correct that r is large, the left side is large and likely to slip. So that's the idea there. And so the coin will slip when it's too far, but their reasoning isn't necessarily incorrect. So Blake is saying that if your car is making too tight of a turn, it can slide out of control. That's true if you're trying to go too quickly. But in this case, in our example of a turntable, the turntable is setting the speed essentially. So the closer you are, the less quickly it's moving because everything has a constant rotational speed. So Blake would be right in our previous problem of a car that can set its speed independent of the circle. With the turntable, the speed is set by the turntable. So in other words, the closer you are, the smaller v will be. The farther out you go, the larger v will be. Carlos has some incorrect stuff in that there's never any force pulling you away from the axis. So I do want to point out that both of them have correct thinking and both of them have incorrect thinking. But if we look at just the inequality, we can see that Carlos's conclusion is correct even if his reasoning isn't. And then Angela and Dominique are arguing over the mass of the coin affects whether it will slip or not, and blah, blah, blah. Does it matter? If we look at our equation up here, there's no mass in there, so the mass of the coin doesn't matter, just the coefficient of friction. So if you made the coin out of something different, it might slip because it's a different material and the coefficient of friction might be different. But if it's the same stuff, then that doesn't matter. So that covers both of these. Let me know if you have any questions, but otherwise you can also check out materials for the other worksheets as well.